In this video, we are going to prove the Poincare Lemma. So as a reminder, I'll go back up to the top. So what we're proving is that for k greater than 0, any differential k form on Rn that is closed is also exact. Okay, so our strategy is to show this equality using the maps L, C, and K defined above in the previous video. Okay, so our method will be to show this equality. I'll give it a name star, for the very simplest type of K form. So for alpha, just equal to a sub j dyj. And then on the homework, you'll show that it's true for all alpha. This is a fairly straightforward argument involving the linearity of C, L, and K, and D. Okay, so there's going to be two cases because K is defined in two different ways when the n+1 coordinate shows up or not. So the first case is going to be when j sub k, the last entry in the tuple j, is equal to n+1. So in this first case, we're going to compute the dk alpha term. We're going to do that one first. So dk of aj y1 through yn+1 dyj1 wedge all the way out to dyjk, which jk is n+1 in this case. So now we're going to apply k. So this is d of, so going back to our definition for k, because we do have j sub k equal to n+1, then we're going to be using this formula, the second formula here. So this will be the integral from 0 to yn+1 aj y1 through yn t dt, and then multiplied, or sorry, this is the coefficient of dyj1 wedge all the way out to dyjk minus 1. Okay, now I apply d. So this is the sum from j equals 1 to n+1 of d by dyj of the integral here, this coefficient. And I realize I forgot this parentheses, times dyj wedge, the same form that I had before. Okay, and now because there is no, because the integral only concerns the yn term, I can just move the differentiation under the integral sign for the first n. So this is the sum from j equals 1 to n of the integral from 0 to yn+1 d by dyj aj y1 through yn t dt, and then multiply it by dyj wedge dyj1 wedge all the way out to dyjk minus 1. And then for the nth term, using the fundamental theorem of calculus, I get that this derivative is just a sub j at y1 through yn+1 times dyj. And I actually have to add one last sign. So what's going to end up happening is I get a -1 to the k minus 1, because this yn+1 term is going to have to travel over k minus 1 times to sort of reset itself, this differential form to look like dyj. Okay, so that's the dk alpha term. Now let's compute the k d alpha term. So here I'm applying K to D of the same thing. So first I apply D. So first I will differentiate j equals 1 to n plus 1, d by dy j, aj at y1 through yn plus 1, dyj, wedge, dyj1, wedge, all the way out to dyjk. So again, because j sub k is n plus 1, this is going to, so dj sub k is dy sub k is dy sub n plus 1. And so when j is equal to n plus 1, we're going to actually have two dy sub n plus 1 terms. So this whole thing is just equal to the sum from j equals 1 to n of d by dyj a sub j y1 through yn plus 1 times this differential form. So I just can't, I'm not allowed, I sort of, basically because I know what one of my y sub j's is, I know that I know that dy sub j sub k is dy sub n plus 1, so j can never be n plus 1. Otherwise, I just get 0. So now I apply k to each of these terms, and the first thing that I'm going to do is rely on the linearity of k, which is something you're going to show on your homework. But basically, I can put the k underneath the sum sign. And then what I'll do is I will integrate from 0 to yn plus 1, d by dyj, aj, y1 through yn, t dt, dyj wedge, dyj1 wedge, all the way out to dyjk minus 1. And I think I need another, oh, no, I had that one already. Okay, so now let's subtract these two terms. So dk alpha minus k d alpha is equal to this thing minus this thing here. And the first thing to notice is that I see a bunch of terms which are just going to cancel each other out. In fact, all of this is going to be canceled by all of this. So what I end up getting is just the -1 to the k minus 1 times a sub j y1 through yn plus 1 times dyj, which is just -1 to the k minus 1 times alpha. So our goal, remember, was to show this equality here. And to do so, what I've shown is that this part is equal to -1 to the k minus 1 times alpha. So the goal now becomes showing that alpha is equal to CL alpha plus alpha, because -1 to the k minus 1 times -1 to the k minus 1 is just alpha. So this is equivalent to showing that CL alpha is equal to 0. CL alpha is not going to be equal to 0 in general, but just in this case, it will be. So in fact, L alpha is S pullback of alpha. And we're thinking of alpha as just being a single term, a sub j dyj. So this will be a sub j composed with s times, as the coefficient in front of, ds pullback yj1 wedge all the way out to ds pullback yj. Okay, but jk is equal to n plus 1, and S is the stretching map. So S pullback of yjk is just equal to the 0 function. So the pullback of the function yjk on Rn plus 1 is the 0 function, because when we do the stretching map, right, we're just including Rn into Rn plus 1 as the first n coordinates. I can also compute this because S sort of ds is just going to be equal to the identity matrix, but with some extra zeros added to it. So it'll be like the identity, the n by n identity matrix, and then a row of zeros. So I can then compute the actual pullback, which will pull back dy sub n plus 1 to 0. So L alpha is 0, so CL alpha is actually 0 as well, and we get what we wanted. Okay, so now for case 2. J sub k is not equal to n plus 1. This case is slightly faster because k alpha is equal to 0, right? Because k alpha is only non-zero. If we go back up to the definition, it's only non-zero if j sub k is not equal is equal to n plus 1. If j sub k is not equal to n plus 1, we just get 0. So going back down here, we're just going to get k alpha is equal to 0, so dk alpha is also 0. So now all we need to do is compute k d alpha. So this is again k of d alpha, which is the sum from j equals 1 to n plus 1 d by dyj a sub j at y1 through yn plus 1 times dyj wedge dyj1 wedge all the way out to dyjk. And now this is only going to be non-zero if j is actually equal to n plus 1, right? Because there are no n plus 1s amongst these j sub 1 through j sub k. So, and k is only non-zero if one of the d sub y's is d sub yn plus 1. So this one had better be d sub yn plus 1. So this is just k of d by dy n plus 1, aj y1 through yn plus 1, dyn plus 1, wedge dyj1, wedge all the way out to dyjk. And then using linearity of k again, I need to move this over k times. So this is -1 to the k dy d by dyn plus 1, aj of all of the same things. But now instead, I've moved my dy sub n to the end, dy sub n plus 1 to the end. So now this is -1 to the k times the integral from 0 to yn plus 1, a sub j y1 through yn t dt, and then times dyj1 wedge all the way out to dyjk. Okay, so now what I need to do is apply the fundamental theorem of calculus sort of in the other way to get that, oh, right, and the reason why this is confusing is because I forgot to put in, I forgot this little, let's see if I can fit that in there. Yes, I forgot the little d by dyn plus 1. So using the fundamental theorem of calculus in the other direction, this is -1 to the k times aj y1 through yn plus 1 minus aj at y1 through yn 0 all times dyj1 wedge all the way out to dyjk. Okay, so now what we have is we want again to show our equation. So this same goal. So here I can plug some things in. So dk alpha is 0. And, oh, sorry, this should be a minus sign. I think I've been saying it's a minus sign and using it as a minus sign throughout, but I wrote a plus sign. Let's double check. Oh, yep, I did it again here. Okay, so if we go back to what we were doing, so this is just going to be kd alpha, which is -1 to the k, aj dyj, minus aj at y1 through yn, 0 times dyj as well. So I can rewrite this as alpha equals CL alpha plus, okay, so now -1 to the k times another -1 times a -1 to the k plus 1 is just now a wash, right? They all are just pluses. So this should become alpha minus aj at y1 through yn, 0 dyj. So I can cross off the alphas, and it remains to show that CL alpha is equal to aj at y1 through yn, 0 dyj. This is all I have to show to finish the proof of the Poincare lemma. Okay, so first let's compute L alpha. This is again aj composed with s times dx j1 wedge all the way out to dx jk, because if x, so this is using coordinates x1 through xn on Rn, basically because s is the identity on the x coordinates and then adds an extra 0. So then CL alpha is just equal to aj composed with s composed with p, and then now all of these coordinates just get switched back to being y's, because none of them are the, well, essentially, none of these in the first place were the n plus first coordinate. So it sort of is the identity on, this composition is the identity on whenever there are no dy sub n plus 1s involved. But now consider what s composed with p does. S composed with p of y1 through yn plus 1 is s composed with y1, s at the point y1 through yn, which is just y1 through yn, 0. So this is exactly a sub j at the point y1 through yn, 0 dyj, which is exactly what I wanted to show, and we're now done.